Actually never did a progression about perpendicular bisector. I don't want you to think about it like that because we're not doing proofs with this. But what I want you to think of is what does a perpendicular bisector do? We're not trying to right now. What does a perpendicular bisector do? It bisects what? Bisects not a line, but a segment, and then it is perpendicular to the segment, right? So if I just draw this, if I take any segment, and if I'm going to draw the perpendicular bisector, does it matter how long that segment is? No. We know that we get a right angle, and we know that this happens. Now, whatever length this is, whether it's short, whether it's long, or whatever, does it have any bearing to the problem at all? No, but watch what happens. If I have this perpendicular bisector, isn't it reflexive to itself no matter what?
Yes.
No matter how long it is?
Yes.
So what do you have without drawing those other sides? Try again. Just side and side. Notice going on both sides here, you've got a side, an angle, and a side. A side, angle, and a side. So no matter what, perpendicular bisectors create isosceles triangles. They will create an isosceles triangle because you get that side angle side right off the bat, which means anywhere you put a line on here to connect it back, it's always going to be the same distance because of CP/CTC. So no matter what, that's what happens. So anytime that you have a point that lies on a perpendicular bisector, it's always going to be the same distance to the endpoints. They call that equidistant. Basically, just think of it this way. You're always going to create these isosceles triangles out of it because of side and side. That's about it. Not really difficult, is it?
Yeah.
So there's two different things. Perpendicular bisector. If you are on the perpendicular bisector, you are equidistant to the endpoints of the bisected segment. That's that diagram we just drew in so many words. That's the diagram we drew in not so many, I should say not so many words. Okay. Excuse me. You could have charged yourself at home. You won't get long for a week.
I never got a chance.
Remember, if you're the perpendicular bisector, you're perpendicular and you bisect the segment. This, no.
Can't follow in some.
Complementary is when you have two angles that add up to 90. We're not dealing with angles. The right angle is what's formed here. Okay. So these two guys are always going to be the same. You always get a right angle, and no matter where you place yourself on this line, it's always going to be a reflexive segment. So these coming down this way are always going to be the same. Just remember that if you're on the perpendicular bisector, you're basically creating isosceles triangles. Okay?
You basically have as many isosceles triangles as you want as long as it's perpendicular.
Yeah, because wherever you place yourself on that line, you can draw it back down. It's going to create an isosceles triangle. Okay? Now, it works the same way going in reverse. If you're equidistant from the endpoints, you're on the bisector. That's it. Not a lot of craziness here, guys. It is relatively straightforward. Okay. Let me show you an example. It is quite literally, they will tell you that you have something that's been that has a perpendicular bisector to it. It'll say that something happened. KM is the perpendicular bisector of JL. Well, if that's the case, all you have to do is mark the diagram to show what parts are equal to each other. Solve for x, solve for y, that's it. Because remember, whenever you have perpendicular bisector, it creates this type of an image. Okay? It creates excuse me. So if I start this out, knowing that I have a perpendicular bisector, we have the right angles here. Let me change colors. We have those right angles. I know that these two are going to be the same because that's the segment that was bisected, which means these two have to be the same because this is the bisector. Algebraically, solve for x, solve for y. Okay. Oh, and I know that I think there was a couple. I know, Jess, I think you were the only one that has still have to do that test. I'm sorry, I was going to have you do it last Tuesday, but due to circumstances beyond my control, can we do it tomorrow? Is that all right? I was going to make you do it today. Is that just the way it goes? Oh,
I found it.
never mind
I
then.
did it.
Yes, it's in the.
Yes.
Congratulations. Thank you for paying attention. Unless you want to take it again and see if you do any better.
I would.
So algebraically, it's just this. 2y plus 9 is 5y. What do you do? Yeah. 9 is 3y. What's y? Done. What do you do with the x? Same basic idea. Yeah, two-step algebra problem.
And then if you're gonna find JK, what do you do?
Yeah, just substitute back in. Very good. Yeah. And that's what happens a lot of times in this. They'll just ask you to find a certain part using the definitions and just fill in the blanks. So you have 4x, and you get 4. Okay. And that's what this stuff works with. I don't need to be that over-caffeinated. All right. Try to blow that up for you. Take a second and try this one. Yeah, seriously, once you know that you have the perpendicular bisector, you know this happens. This is a reflexive side, which means that these have to be the same. And you just go through it like that. This is basically using side angle side to show that you have CPCTC, and then just use the algebra. So you're using what we did back a month ago with proof stuff, just algebraically, really. So it's a matter of setting them equal. 2y plus 15 is 9y minus 13. That's a 13. Did I say 15? Oh. Move stuff around real quick. Add the 13, subtract the 2. You get, what is that, 28? Is 7y. Y is 4. So if y is 4, substitute back in. What's 2 times 4? Yeah, 8. 8 and 15 is? Use a calculator, ladies and gentlemen. I said 8 and 15. Do the same thing with the for the other stuff for x, find x, y.
Right over here, I'm gonna like to go right
And you get 10. Okay. Ladies and gentlemen, if you have not done so already, remember we are selling calculators. We have plenty of them. Please, 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 please make sure you get one soon. You need to have a calculator, like all the time now. Because every day is algebra stuff, so you know. Okay. So what happens here now is that we're just talking about being on a perpendicular bisector. If you go back and think about an actual triangle, though, if you have a triangle, if you have a triangle, how many sides does it have? Three of them. Now, that means that in the triangle, the three sides could have how many perpendicular bisectors?
2.
How many sides are in a triangle? Three of them, which means how many perpendicular bisectors could there be? 3 of them. Yeah, obviously. So if I say this is going to be the perpendicular bisector, it would be here. Oop. I'm not drawing it all the way through, though. Are we okay with that? I'm just kind of guesstimating about halfway. Draw another one. About here. Let's do like this. Don't do it a little lower. Let's see this. Sure. Here's our right angle. And then we have another one here. I tried to make them all neat.
That's a really small triangle.
So you could have 3 perpendicular bisectors inside of a triangle because there's 3 sides. These 3 perpendicular bisectors could meet at one specific point in the triangle. Actually, it could be at a couple of different spots. Where 3 or more things run into each other, it's called a point of concurrency. Weird name for this. A point of concurrency. I don't know if there's 2 R's or not, but close enough. There's a point of concurrency, and this is kind of what we're going to look at. When we're talking about, these next couple of days here, perpendicular bisectors, angle bisectors, and medians. They're going to have these 3 things that are called points of concurrency. It's where these segments meet inside of a triangle, or actually meet outside, but we'll get to that later. And within this point of concurrency, you get specific values that occur. Whether it's going to be, you're going to have certain segments that are going to be equal to each other, okay? And it's a matter of keeping this vocabulary part straight. And this is where it gets a little bit tricky in chapter 5. The math part is easy. It's 2-step equations left and right, it's just a matter of setting things up. Keeping the vocab straight as far as what these points, what are called points of concurrency straight, is what gets a little messy. So here's what happens. You get this thing called a point of concurrency. The point of concurrency, let me draw this out here. If we look at a triangle where you have these 3 perpendicular bisectors, they all met at this point P, okay, inside that triangle. That means from vertex to point is all the same. So inside of perpendicular bisectors where they all meet, there are 2 R's. Okay? This point where they all meet, the segment from that point to the vertex, point to the vertex, are all congruent. Okay? So in a perpendicular bisectors where we have and I just had a bunch of markers. I forgot to took them out of my bag. Whenever we have these, it's these 3 segments here. Point to vertex. They're all going to be the same. You know what happens when you run out of tick marks instead of using 4? You probably saw me do that. Sometimes people do that. It means the same thing, where you put that little V instead of putting 4 slash lines on it, just because it's less messy. That's one of the reasons why we do that. So you get to this point, these segments are all going to be the same. Also notice, what happens is you get 1, 2, 3, 4, 5, 6 different right triangles. When you see right triangles, what happens a lot of time? Well, what's that one crazy theorem that we've used but we've never talked about? The Pythagorean theorem. Okay. It's crazy that they anticipate the fact that you remember the Pythagorean theorem, but yet they don't discuss the Pythagorean theorem in the book until you get to chapter 7. It makes a lot of sense. So we're going to go on this whole idea of what's called background knowledge. I believe that's called schema. Am I right? Is that right?
Recent college grad or what?
I'm something. It was funny that I was cleaning out the basement. We were cleaning out the basement so we could start framing it and all that over Christmas. And I found some of my old college stuff. And there's a project that Severino and I did in college in the spring of 2005 that we have our full write-up of this lesson plan, the activity that we did for geometry. Guess what we still use to this day? Same thing. Yeah. We still use it. Every year we use the same thing. It's the clinometer one where you're measuring with the, yeah, we still use it. It's a great activity. It's awesome. We got an A on it.
I've got a quick question.
I'll show you. I brought the write-up for it downstairs. Yes, sir.
When did you graduate college?
From college? 06, I think?
So you
I feel.
About what?
how about 90s?
How young are you?
How young am I? 32.
Oh, I thought you were 90s.
But remember, I started late. So I started late.
Remember, he's just making excuses.
No, I didn't want to say how old are you to make you feel old.
So this point
Did you hear that one?
This point is called the circumcenter.
Wait, what?
That point where all the perpendicular bisectors run into, it's called the circumcenter. We're going to have 3 different names. We're going to have circumcenter, incenter, and orthocenter.
So incenter is in the inside of the triangle.
This point where they meet, it's called the circumcenter. That's
It
all.
sounds right.
Yeah, where that point of concurrency, the specific name for it in this case is called the circumcenter.
So forget points of
Well, this is a point of concurrency where all those things run into each other. It just says it has a specific name. It's called that. Yes, sir.
So is incenter is the inside of the triangle and whatever the other one was is the outside of the triangle?
No, incenter and orthocenter deal with angle bisectors where the 3 angle bisectors meet or where the 3 medians meet. And we'll talk about that tomorrow on Wednesday. And that's kind of the idea of the vocabulary. The circumcenter goes with perpendicular bisectors, and its point converts that circumcenter. That's what we're going to get at here. So, that's kind of what you need to know. Really. What's it called and how do you use it? Because in instructions and stuff like that, it'll say at some point in time, shh, gentlemen, point R is a circumcenter, and you'll have to know what to do. Point S is an incenter, you'll have to know what to do. Things like that. That's basically what it boils out to be. There's only 3 of them. Once we figure that through, you're going to be all right. Okay. So let me show you this. Not worried about that. Let me show you how this is going to work with an example that you don't need to draw. Because that would take forever. Sir?
The Warriors won.
Yeah, don't draw this. That's just silly.
They win.
Takes too much time.
They won. Hey, aren't the Lakers and the Warriors all coming to conference in the division?
So what is M O be 26? I was just asking, calm down, big fella.
Hey, the Warriors, something. Clippers. Hey,
Definitely something. We have enough ball? You
Warriors, Kings, Clippers, and Trailblazers.
know, I don't like the crowd. Too much work. Too much work. No. So basically, here's what happens, guys. They tell you that in the diagram, all the perpendicular bisectors meet at that point O. That means point O is the circumcenter. Okay? So that also means then, in the diagram, there's a couple of things you can mark right away. You know that the perpendicular bisectors create this, this, and this. Everybody okay with that? Just by starting with the big picture. You also know that you have right angles here, here, and here. Now, Whiskey pointed this out a second ago when he was walking around. Whiskey, what did you notice?
Oh, did I notice something?
Yes, you did.
MO would be 26.8 and PO would be 26.8.
Because why?
I don't know. Let's just guess.
Because it's the same as NO.
Because they're the oldest, they're all bisected.
No. They're all coming from the same. They're all coming from the same point. They're coming from that what's called the circumcenter. So when you're at this point O, from this point to all the vertices are always going to be the same. So I'm going to make this little V tick mark here. So like you said, each one of those three winds up being 26.8. Okay. You also have all these other segment parts that you can fill in. Bless you. For example, what is PR? 26. What is SP? Why is it 26? Because that's 22. And QN is 20. If I'm not mistaken, we haven't even looked at one of the questions yet. All we did is we went right off the diagram. So now if you go through it, you should be able to figure everything out. What is MO? 26.8. Good. What is PR? It's 26. Everybody okay with that? No, why not? Huh? What about MN? 40. 40, good. SP? 22. QN? And MP? 44. Okay. What if I got crazy and I asked you to figure out what is SO? I know.
Is there a
No.
theorem you can use?
What's that?
Is there a theorem?
Now, if I'm asking you to figure out what this is here, that is part of that triangle. Oops. I'm not dealing with angles here. I have a segment here at 22. I have a segment here at 26.8. And I'm trying to find that. A squared plus B squared is. Now, do you guys remember which one of those is always the C value? The hypotenuse. Where's the hypotenuse always
So
located?
it's 26.8
Across the right angle, right.
minus 42.
Hold on. This is always your C value. It's always going to be across from the right angle. That's always the hypotenuse. So algebraically, what you would do then is, I'm going to put this on a clean oops. Bring this out eventually.
So C squared minus A squared should give you B squared.
Yes. All right, there. So then you know that x squared plus 22 squared has to equal 26.8 squared. Again, this is why it's important that you have your calculator, because you can do one of two things. I could press my squared buttons and rewrite the equation, or x squared is going to equal 26.8 squared minus 22 squared. All I did was just move that over, just by subtraction, just like you would normally. Now what I have to do is put it in my calculator.
Is that your grandkids?
What's that?
Is that your grandkids?
Yes, those are my grandchildren.
They are parents from like.
So when you type in, once this loads up, my calculator is awfully slow on here. I'm gonna steal yours. You're the best. So you type in 26.8 squared. Oh, 26.8 squared. Subtract 22 squared. I get 234.24.
Somebody stole mine.
How do you undo squaring? Square root. Do you guys know how to do the shortcut of square rooting of an answer?
Yeah.
We're gonna do this a ton in here.
Yes.
How?
Alright. Press second,
Okay.
into press squared.
Uh-huh.
Oh.
Where's your calculator? Okay.
Somebody
So if
stole
you
it.
hit second square root like you would normally, and then hit second answer, which on this one is your negative symbol, it's gonna, on the screen, it's gonna say square root of answer, and hit enter. What it's doing is it's taking the square root of 234.24 without you having to retype it. Okay. And that's how that would work. So if we had 234, you hit second square root. And I'm getting 15.3. See if my calculator still hasn't loaded.
Maybe it's broken link.
No, there it is. Now, like I said here, guys, we had 26.8 squared minus 22 squared. All you have to do is you hit your second square root like you would normally. My answer button's in a different spot than yours is, but your answer, I believe, is on the negative symbol. You hit second. Oh, mine is in the same spot. Sorry. I thought it was on the enter. And then you just hit enter. And it automatically takes the square root of the last thing you had up. Okay? It's a lot easier to do that a lot of times instead of trying to rewrite and retype. Okay? Being able to utilize your calculator to find these, to use this answer button a lot, it's going to help you tremendously when we get to trigonometry, because we do this a lot. Okay? Questions about this?
When we get to what?
Hmm?
When we get to what?
Trigonometry. When we start using sine, cosine, and tangent, you'll be taking square roots of answers and sines and inverse sines and all that stuff. So,
And when's that?
January-ish, February.
I thought I signed up for geometry.
It is geometry.
No, it's not. It has
2 parts homework here. This is in section 5.2. It's in the book. I should have to write the section here.
But isn't that what you said about the calculator?
If I'm not mistaken, those last problems there is an example of what we just did using the big picture diagram. Yeah, 317, okay, and 09. I don't know why I have this 309 here. Sorry, this isn't correct.
Good thing I didn't write it.
Yeah. No, I don't know why I had that on there. I might have had something else typed on there from a while back. No.
So just the first part?
No, she's looking for more. I know.
Yeah, that's all you need. Okay.
Oh,
Oh, alright.
Yeah, just got 3 through 17, okay? Yeah, I don't know why I had that on there. It's not even the right page for anything.
What's the day, Mr.
Today's the 28th.